Hey, welcome back, Marauders. This is the second part of video 3.4 on the ideal gas law. This section is about Dalton's law of partial pressures. It's my favorite section, so let's get started. So Dalton's law of partial pressures says that the total pressure in a container is equal to the sum of all the pressures of all the other gases if they were each alone in the container. So you can see in my example over here, we have gas A, B, and C, and they're all in separate containers of the same volume. And if we knew what the pressure of each one of these gases was in these similar sized containers, and then we put them all together, the total pressure in that new container would be the sum of all the partial pressures. And so it looks like this. The pressure total is equal to just the sum of all the pressures that the individual gases would exert if they were just in that container by themselves. We can also do it as a proportion. So it says that the partial pressure of a gas is proportional to the mole fraction of that gas. So if half the particles are from gas A, then half the pressure is coming from gas A. Let's do a sample calculation. A tank contains 2 moles of oxygen and 5 moles of carbon dioxide. The total pressure in the container is 956 torr. What is the partial pressure of the oxygen? All right, so in this problem, we know the total pressure is equal to 956 torr, and we want to find the partial pressure of the oxygen. We also know that 2 moles of oxygen and 5 moles of carbon dioxide. So we can calculate the mole fraction, and we know that 2 out of every 7 particles are oxygen. We're getting the 7 just by adding up the total number of moles. 2 moles of oxygen plus 5 moles of carbon dioxide. So we have 5 moles of gas total. So since 2 out of every 7 particles are oxygen, then 2/7 of the pressure should be coming from the oxygen. And so we're just multiplying the total pressure by 2/7. That's the mole fraction of oxygen. And we get the partial pressure of the oxygen. The other time when partial pressures are pretty important is with the vapor pressure of water. So it's a pretty common laboratory procedure to capture gases over water. So here's a chemical reaction taking place, and then the gas bubbles through some water and gets collected in this container above the water. Well, when you collect gas like that, it's pretty good because the water holds it in, and so we can easily measure the volume of the gas, and it's not going to escape. However, we do need to account for some of this water evaporates and turns to gas. So a little bit of the pressure inside of this container is not from the gas that was created in the reaction, but it's actually from the water vapor. And so this is like Dalton's law of partial pressures. The total pressure is equal to the pressure of the gas that we're actually interested in plus the partial pressure of the water. So typically what we'll do is we'll look up the partial pressure of water, and then we'll subtract that from the total pressure to get the pressure of the gas that we're interested in. I'll show you an example. So here's an example. Nitrogen gas is collected over water. So that would be in an apparatus like I showed you in the previous slide. And it's at a temperature of 30 degrees, and the total pressure is 750 milliliters of mercury. If 0.35 liters of gas were collected, how many moles of nitrogen are in the container? All right, so it's an ideal gas equation. PV is equal to nRT question. But first, we need to look at the pressure. So we have the total pressure. We don't have the partial pressure of the nitrogen yet. This pressure includes the water vapor and the nitrogen gas. So what I want to do first is I want to subtract out the partial pressure of the water vapor. So it's the total pressure minus the partial pressure of water gives us the pressure of just the nitrogen, the gas we're interested in. To get the 31.8, the partial pressure of the water vapor, what I'm doing is looking at this chart right here. And so it depends on temperature. At low temperatures, not very much water evaporates, so it has a low partial pressures. And then as the temperature increases, the partial pressure increases because you have more particles of water vapor. But we're at 30 degrees, so we just follow the chart over here, and we have a partial pressure of water vapor of 31.8. So that's why I'm subtracting 31.8, because of that total pressure, 31.8 of it was coming from the water vapor, and the rest was coming from the nitrogen. Once I have the partial pressure of the nitrogen, I'm just converting it back into ATM so that it matches up with my units on the gas constant. And then here are my other given information from the problem: the volume of the container, the temperature, which we converted to Kelvin, and then the number of moles is what we're going to try to find. So now I'm going to plug everything into PV is equal to nRT. Again, when I plug in the pressure, it's not the total pressure, but it's the pressure of just the nitrogen after I've subtracted out the water vapor. Then we're just using algebra to solve, and we get the number of moles of nitrogen in that sample. All right, that's it for this section. Make sure you practice these types of problems.